Yes, so I'm going to try to explain the motivation in this paper. So if you consider some manifold with a Riemannian manifold with a metric G, and you consider a differential equation, ordinary differential equation on this manifold, then there's the so-called contraction theory. So this contraction theory is based on ideas that have been around for a long time. It's been popularized by Jean-Jacques Slotin with a paper 20 years ago with Lohmiller. And so you can want to look at Slotin's work. There's also recent work by Rodolphe Sepulcre, who is attending the conference. So we say that F is a contraction, so the field which defines the ODE. F is a contraction or infinitesimal contraction if it tends to contract, the flow is contracting, which means that if you take the derivative, covariant derivative of F with respect to any, so V, so X is a point in the manifold, V is a tangent vector at X, and so for any X and V, you have this scalar product with V with respect to the metric G is less than minus lambda norm of V square. So what this equation means is that if you take some initial condition here, X, then you have a flow associated to this equation. So you have f of X is a tangent vector. If you move in the direction of V a little bit, here, then you will have another point which is infinitesimally close, and the distance, the infinitesimal distance between those 2 points under the flow of this equation tends to be reduced, to decrease with a rate which is lambda. So this is something that you can check by just first order properties of F, and the result is that you have a contraction theorem which says that under condition on the manifold, or the set on which F is a contraction, you have this. If phi t of X is the flow of this equation, meaning that X is the initial condition and this is the solution of this ODE at time t, then the distance, geodesic distance, between phi t of x0 and phi t of x1 is less than this. So it means that you have a contraction, the flow tends to contract, so the distance between the solutions starting from 2 different points at time t is less than something exponentially decreasing times the initial difference. So this is the usual picture. You have 2 initial conditions, and F is a contraction means that the distance tends to decrease exponentially. So how can we use that? So it's useful in several areas. especially for observer design. So now our first problem, so all this is non-results, would be, imagine that I have some contraction over a manifold, and this is a physical system that I'm interested in, and I want to estimate the state. So x of 0 is unknown, and I would like to have an estimate of x of t, the internal state of the system. So how can I do that? Well, if f is a contraction, it's not very difficult, because I can take any initial condition, something arbitrary, and then, thanks to the contraction theorem, I'll have that the distance between, okay, so, and then I integrate the equation. So I implement this equation, the equation of the system, on a computer. And at time t, the distance between my estimate and the true trajectory will be less than exponential minus lambda t times the initial distance between my estimate and the true state. So this is called a naive observer, because I just integrate the equation of the system, and thanks to the fact that all the trajectories converge to each other, after some time I will have a very good estimate of the true state. So there are examples, engineering examples, where this can be done, and one of the most famous is a chemical reactor. So it's a famous model for chemical reactors. So it's the exothermic chemical reactor, and here are the equations. So it's a paper by Adebekun and Shork from 1989, but it's very well known in process control. So you have various concentrations. So the equations are made of mass balance. So I is some concentration that you want to estimate of reactive inside the concentration. This is the time derivative of I is what goes in minus what goes out of the reactor minus what disappears into the chemical reaction. So you have an Arrhenius term, RT. T here is the temperature that is assumed to be measured by some temperature sensor. Then there's another concentration with a similar equation. So this is known, this is what I inject in the reactor, minus 2 Kp, an Arrhenius term again, T of T, and then here I have some nonlinear term that involves M and I. And then I have a third reactive which follows a similar equation. So this is a nonlinear model, meaning that I cannot use, well, I mean, anyway, the only thing I measure is temperature, anyway, how do I have access to those concentrations? A priori, I don't have access to them. I don't have concentration sensors, and the measurements I have are not sufficient. But here, it was proven in the Slotin's paper of 1998 that this is a contraction. So now the manifold would be R3. The matrix is just the standard norm, Euclidean norm on R3, and this is a contraction. Okay. So this whole model writes like this. And if I implement on a computer a naive observer, so I just copy the dynamics with some arbitrary initial condition, I am. Then, thanks to the fact that it's a contraction, after some time, I will have a very accurate estimate of the concentration inside the reactor, and I will be able to track them. So if the flow here varies, if the temperature varies, if everything varies, since F is a contraction when I fix time temperature, then I'll be able to track the concentrations, because those estimates will tend exponentially to the true concentration. So this is known results. It's been known for 2 decades. I mean, known and used for 2 decades. So what is now the problem we consider in the paper? Assume that we have something a little different. Assume that, for instance, we don't have access to perfect measurements of the temperature. Okay, so now our problem 2, this is the one we consider, would be the same estimation problem, but T is measured at discrete time. I don't have continuous measurement. At times T1, T2, T3, etc. So between 2 measurements, I don't know what the temperature is. So I cannot integrate this. Moreover, the measurements are noisy. So this is some random quantity which represents uncertainty in the measurements. But I have some enthalpy balance which gives me a dynamical model for the temperature as well. So now I can add another equation here. I have a time derivative of T is equal to some function of T, let's say, plus some noise. So this would be white noise. So this would represent the uncertainty in my model about the evolution of temperature. So it's a quite different problem, because when I measure the temperature, I'm wrong. I measure it up to some random variable that I don't know. And moreover, even if I measured it perfectly between 2 measurement times, if I integrate the model for the temperature, which is given by some enthalpy balance, then I have uncertainty as well. So when I'm going to plug my estimate for T in this equation, it's not going to work, because this T is going to be different from this one. So now I have an estimate as well for T. I don't have the true T. So what can I do? So the idea is to inspire from particle filtering. In fact, just with those equations, this equation for the temperature and those measurements, I could build a particle filter and would give me some estimate for the temperature, and I could plug that in there. But this is not what we did. We did something which is very close to that. So I'm going to be very vague about particle filtering. I don't want to get into too much statistics, but just to give you the idea of how it works. So we make a particle filter based on the fact that, based on the observation that conditionally on T, model is a contraction. So in fact, this dynamical system is a partial contraction. If T, the temperature, is known, then it's a contraction. So the idea of particle filtering in this case would be, okay, I'm going to try a lot of possible T's here. For each of them, if I'm right, then by just integrating the equations, I will recover the true concentration. For some of them, I'll be wrong, but hopefully, in all the particles I'm going to have on the temperature, some of them will be true, will be very close to the true one, so that contraction will work and allow me to estimate the remaining variables, which are the concentrations. So I take some particles, T1, T2, etc., Tn, so I have n particles. Each particle is an assumption on the temperature. For each assumption on the temperature, I can integrate these equations. So I get for each assumption an estimate of the concentration, I, M, P, and so on. So I have 3 more variables for each hypothesis on the temperature. And this gives me candidate estimates. So what I do then is that I devise a particle filter. So just let me give you the algorithm. I'm almost finished. So between two measurements, integrate model equations. So you simulate this model for each particle. So this is a noisy equation. So you simulate this by using some realization of your white noise. You also integrate those equations. When the measurements arrive at time, say, Tn, evaluate likelihood of each particle by comparing this temperature, for instance, for particle 2, with the measured temperature. Duplicate particles that are likely and kill the ones that are unlikely. So this is how particle filter work. So what do you have at the end of the day? You have, this is the temperature over time. Assume that this is the true temperature in the reactor. You initialize some temperature, and then you integrate. So those are your particles, so it's candidate trajectories for the system, and you integrate this model for temperature by simulating white noise. Then, for each of those temperature, by integrating the remaining equations and plugging the candidate temperature in them, you have some, so this is concentration. You have some estimate for the concentration, which are those guys here. So you have 1 for each candidate temperature. When the measurement arrives, you can evaluate the likelihood of all your particles and only focus on the ones that are the closest to your measurement in some statistical meaningful way. And the idea is that if by chance you have sufficiently many particles close enough to the true temperature, Then thanks to contraction, the estimate here you have. So this is the corresponding concentration to the true temperature. If you take some simulation of your system which is close enough, then thanks to contraction, the remaining, if the temperature is close, the remaining estimate will converge to the true estimate for the concentration. So by having this structure of partially contracting system, you can hope that you run a particle filter on the variables that are not part of the contraction system, that make the system not a contraction, and then conditionally on those variables for which you have Monte Carlo estimates, then you know that you have a contraction, so the rest is well behaved. So this is the idea we used, and we did some simulations. It works well, so we did some simulation with this chemical reactor. Of course, we have no proof of convergence whatsoever, because when you use particle filters, there are not many proofs of convergence. So, but maybe this could be investigated in the future. Thank you.
Other questions for the speaker? Yes.
So I don't know a lot about particle filtering, but how do you choose the number of the filters, of the particles, in fact? Yes. I mean, is there any...
Well, it depends on the limit of your filter.
Okay.
As many as possible.
But I mean, I mean, practically, if you want to, for example, to... Yeah.
So this is also another advantage of this method. Right? Take particles on all the variables. But then I will have I will need a lot more particles. Here it's particles only for 1 dimensional estimate. So you can imagine that here, if I kind of cover the space which is around the temperature, because you have range for temperature. You know that it's not like 1,000, 100,000 degrees. So you have a range. If you manage to cover this range of particles in 1D, it will be fine. So typically 100 particles will be sufficient. But it's nothing.
Okay, thank you.
More dimension, you can adjust on dimensionality. So by using contraction for some variables, it also allows you to reduce dimensionality.
Another question? Yes?
Is the word naive observer, does that really just mean open loop observer?
Yes. I mean, in my vocabulary, yes.
In mine as well.
So open loop observer.
Other questions? I would have a... Oh, yeah.
Yeah, it might just be a dumb question about the contracting property, but how do you physically explain that there is no importance on the initial shift? Because if there is a limiting trajectory, I can take the same trajectory, the limit trajectory plus a threshold, an initial threshold h, and we know that x of t and x of t plus h are going to squeeze also to contract and to have a vanishing distance between them. So how do you explain that? Does it mean that you converge to a point, or?
No, you don't have to converge to. I mean, here. So if you take this system and you assume that the temperature is measured, then it doesn't mean you converge to. So if everything is fixed, those quantities, the input concentration, the flows here, and the temperature are fixed, then you converge to a point. If they vary, then you can have some limiting trajectory which is time varying.
Okay, but so if I take the limit trajectory, I call it a of t. Then I take a of t plus 1, let's say.
I understand, but you don't do that. I mean, you're running that in real time. I mean, there's no...
Okay, okay, so it's non-autonomous. It's non-autonomous. Okay.
No, it's not. And when you're trying to make an observer, so estimate the internal state of the system which is not autonomous, this is particularly difficult.
Okay.
And with contraction, it's as simple as if it were autonomous. This is one of the main interests.
Okay.
Okay, I think since we are a little bit late, we will stop for the questions now and go to the next talk. So thank you again to Sylvia for his talk.